Okay, so welcome back into Astro Mode, and today we are going to start a project that we introduced last time. Yes, and that is to build my own direct drive mount. Yes, and I was going to start the project by making a direct drive StarTracker, such as this. But it's not a direct drive StarTracker. This is a regular StarTracker with a geared motor that is driving the output shaft in one sidereal rate. Yeah, that's basically one turn, 23 hours and 56 minutes. Or you have actually different kind of settings on this for like sidereal rate and solar rate and polar rate, moon rate, etc. But anyway, so what you do is that you attach your camera, something here, and then you have this mounting configuration, whatever you have. You align the main axle here with the celestial pole using, for instance, the poloscope, and that is the Earth rotational axis. Yeah, that means that basically anything you have attached here pointing at an object in the sky, you turn this in one sidereal rate, that will counteract the Earth rotation, and the object will appear to stand still. Yeah, you're not going to stop the Earth spinning. No, life on Earth will still be the same. You're just going to stop the apparent movement of the object due to Earth rotation. Yes, that's it. So anyway, and yeah, so that's a very simple, neat little way to take long or semi-long exposures of an object in the sky with a not too big, large focal length device. Anyway, yeah. So why make a direct drive version of this then? Yeah, since I have this lovely, nice little thing here. Yeah, wow, it's cool. Really, just need a project. So that's it. So yeah. Also, you have some errors prone to or natural to mechanical systems such as this. One of them is the periodic error. I made a little video on this before. Basically, any axle that appears to be round is actually not perfectly round. No, that means that if that axle is driving something, the speed that it drives that other thing with is going to change depending on where on the axle it is. You have the main motor axis driving gears on the other axis, etc., which means that you'll have a speed variation in your system that is periodic. Yeah. And some mounts you can train for this by basically use a guider and record how the mount moves, and a little bit of a complicated process, all pretty much set up in some more advanced mounts. You can also just use a StarTracker or auto guider to compensate for any speed variations wherever they may come from. But the whole system then becomes a little bit more complicated than you want this to be. You also have backlash. Backlash is basically you have the dead space between gears. So you have a driving gear and a receiving gear, and as long as you're driving in one direction, that's all well and good. But if you change direction, the driving gear teeth needs to move in the dead space between the receiving gear's teeth, before it actually starts moving the other way. Also, you might have a little bit of wobble in your system if you kind of feel on an axle which are geared. You might feel a slight wobble, and that is because of the dead space there that you can move the output axis. Yes. So a direct drive system, and that's just a motor on the axle. That's it. Yeah, super simple. And you have like this period of one revelation. It's 23 hours 56 minutes. And the backlash, there's no gears, so should be what could go wrong? Could possibly go wrong with this? Yeah, should be. Why isn't everything like this? Yeah, well, the direct drive. Yeah, I'm sure we're going to figure that out. So that's it. What I said I was going to do, I'm going to take my hoverboard here with BLDC motors. Yeah, I'm going to take it apart like I have right here. Yes. So we're just going to skip over to that and take a look at what I took out of it, what we're going to use, what we're not going to use, etc. Yeah. So let's go back down memory lane. Okay, so here we can see one of the sides opened up on our hoverboard. It's the motherboard. This particular one has the power input from the battery and the charging circuit on it. There's also a white communication line there that runs over to the other side where you have an almost identical board controlling that motor. These boards also have like the accelerometers and motion sensors for controlling the motor depending on how you pivot your foot on top of it. My idea here was possibly to reuse some of the electronics here. First of all, the drive circuitry. And what I was looking for first here was the main controller, and I found it here. So I basically just traced route where from the MOSFETs, which are the power switching circuits that we can see here. We have 2 for each phase on this 3-phase motor, and so from that I figured out where the output to this circuit was. You can see here, and we're not going to go down this path too long here. I tried it, abandoned it, and decided to basically build my own drive circuit for the MOSFET instead, and tried to make it run that way. Yes. So we're just going to open up the motor instead, just out of curiosity, and take a look at what it looks inside. Okay, so here we can see one of the motors open up. The other one looks just like it. In the center here we have the stator. And that is where you have the motor axle attached to the stator coils that we can see here. It's 27 of them. We have 3 phases, A, B, and C, of 9 coils each. So they are spaced out around the axle here in the pattern ABC, 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 all the way around. Just outside these coils, with a very narrow spacing, we have the rotor magnets. That's 30 of them. Yeah. Now, through the axle, we have a bunch of cables. We have 3 thicker phase cables, that is the power to the coils. But we also have some smaller cables, and that is the Hall effect sensors that we can see zooming in here. And they are sensing the magnetic field from the rotor magnets that we have just outside the coils there. And we can use that information to determine how we want to control the current through the coils to make the motor move in the direction and the speed that we want. There's a bunch of different ways to control a BLDC motor, and we might take a look on some of them here just to understand how it works. Okay then, so I wasn't actually sure of how much I'm going to go into BLDC motor control, but then I realized that this project really is all about BLDC motor control. Yes, that's right, Balti. So I better do some of it. So this motor is using the Hall effect sensors for motion in this configuration as it comes in a hoverboard. And they're using a method called 6-step commutation. Yes. So we're going to just take a look on what that is, just to get a brief understanding. So this is called 6-step commutation. Yeah. So just to illustrate this very simply here, you have our motor like this. We've got 3 phase coils, and they're all connected in the center. Yeah. So this is phase. Let's call them A, B, and C. And around them we have our magnets. Yeah. And I'm just going to show this as 2 magnets and not 30 magnets, because that would be a mess on the board here. So this is our north pole, and that is our south. Yeah. Now, if we want to move this, say, clockwise, this direction, we need to have this magnet configured as north. Yeah. And this coil to be configured as south, so that this is attracted by that magnet and repelled by that magnet. Yeah. Because in this case, I'm going to illustrate this as if I have north, I want to have the current coming in through that coil to the center, and I want the current, in this case then, to go out from the center through the coil and out through the shaft then. Yeah. And if we then carry on with the next step, it's going to be making it very, very simple coils here. Yeah. So this is now A, this is B, and this is C. Still have our stator magnets here. And in this case, I want my A magnet to be north, and I want my C magnet to be south, which means I want the current to come in through that coil and out through that one. So that's step number 2. So step number 3. Yeah, so to make it move clockwise, we now can see in these 6 steps how we need to have the current going through the coils to make it move. Yeah. And when we pass this step, as we can see, we're back to this again. And we can, of course, reverse the direction. We can translate this to a simple table. Yep. Of 6 steps. So we have like 1, 2, 3, 4, 5, 6. Using our phase A, B, C. Now, to illustrate the directions here, I'm going to say if the current is coming in through a coil, I'll give it a capital letter, and if it's going out from the coil, I'll give it a lowercase letter. In through C and out through B. Yep. Number 5, we're going in through C. Yes, Balti? That's what we're doing. And in step number 6, we're going in through B. And we're going out through A. Yeah? And then we're back to normal again. Oh, back to square one. So this is moving a little bit. Yeah, good. Excellent. So that's it. This is like very easy, simple function table that we can have in a program, for instance, to move the motor in either direction in whatever speed we switch between here. And I made it very simple here, so now an electrical revelation is the same as a mechanical one. Yeah. Now, I said we have 30 magnets and 27 coils. That basically means that we have about 15 revelations in one electrical, 15 electrical revelations in one mechanical. Yeah, so it means that we're going through these steps, quite a few of these steps just to go through one mechanical revelation. But anyway, to keep it simple here now, not to dive too deep into this, this is how you do it in, say, a hoverboard and that type of motor where you have the Hall effect sensors. You can also use like current sensing to do the same thing. However, we're not going to use any of this. Yeah, this was just curiosa, just to show that how you do it. Instead of using brushes like you do in a brushed DC motor, you do it this way for just a BLDC motor control. We are going to use something that's called sinusoidal control, or variations of that. So that's what we're going up to next. Yeah, but I thought this was kind of an important first steps to the BLDC control. Okay, so I think we just talked about the 6-step commutation method for controlling a BLDC motor, yeah? And it's a very, very good, simple method suitable for, say, applications like the electrical scooter or a fan or power tool or anything that moving at a reasonably high rate, like a couple of revolutions per minute, for instance, and upwards. For our application, that is way too fast. Yeah, we're moving at maybe, well, 15 over 3,600 degrees per second. That's very slow. And also, if we have a stepped control method, we want the steps to be as small as possible. Otherwise, we'll have a jerking motion. Yeah. So we're going to use a method called sinusoidal control, and I'm going to derive it from this to get it maybe a little bit easier to understand, yeah? And I hope, anyway. So I'm just gonna create a waveform base here, yeah? So this line is +1, this line is -1, this line is 0, and this is like maximum current in one direction, that's maximum current in the other direction, that's 0 current through the coils, yeah? And we have capital A is +1, lowercase is -1, red is phase A, blue is phase B, green is phase C. So I'm just going to transfer those over here. First I'm just going to make a couple of numbers. There we go. So first then, B positive. Yeah. So if this was a 6-step commutation, then we would have, well, discrete step lines through here, but we're going to go past that, and we're going to just connect the dots, yeah? Ta-da! See what's going on? Yeah? If we take another step further there, we'll end up at this point. So basically, you have this moving, connecting to that one. This is, yeah, meeting up there. And then we have this one moving. Yeah. So, it's like a 3-phase sinusoidal function. Yeah, it's just that we got the corners all rounded off nicely. And basically, so this, if I just make a line here, and I sample on each of these, yeah, this is the current draw at this location, at this point on each of the faces, yeah? So that means that this is basically, you could say that this is, if I pull the current that you have in this point in phase A, and the current in that point in phase B, and in that point in phase C, the motor is going to slew to that exact position and be stalled there. It's going to be like a magnetic equilibrium point for the phase coils in the magnetic fields. Yeah, so it will basically be held there, and the force that it's held there with is depending on the current in the coils and the magnets and all that. But yeah, that's basically just like a stall point. And it basically means that I can pick any point on this line. I can pick here, get the currents at that specific location, and then it will slew to that point. Or I can, well, here. Yeah. Well, you see what I'm getting at here. So basically, what's limiting me is basically the resolution I have in the amplitude and the step resolution in timeline there. That's basically my limitations, and it is a limitation. It will limit me at some point, but it will give me a lot finer detail in my motion control than I do in the 6-step commutation. I can go really fine resolution on my motion control. I can go as fast as I like, really. It's just that I can do it in a very fine precision, or I can do it really slow. Yeah, so this is what we're going to be using. Yeah, sinusoidal control of our motor. Yes, and it's really easy. I mean, this is you just pick a sinusoidal function for each of the faces, and you offset. You have one face, and then you offset the other by 120 degrees, and that's it. You can just pick a point, and you will have pretty much this exact spot on all of them. And you can make sure you have the current at that spot. Yeah, does that sound clear, lucid? No, that's it. So we're going to be doing this. There's variations as well. You can have like a modulation, like third harmonic injection, and you can do like space vector modulate. That's the whole science in this, but this is a very good start, and yeah, this is what we'll do. So we'll throw ourselves into the testing and the work of this, yeah, and this is the base function to this is how we're doing it. Okay, so we need to build ourselves a drive circuit for our BLDC motors. First thing we did was that we just took the existing motor boards and just tried to tap into them, use that drive circuit that was on there. Due to lack of control, etc., that was here, we abandoned that and took some protoboard and built our little MOSFET drive circuits. Yes, yeah. So yeah, got us going. Yeah. Okay, so here we can see straight the first trial on moving the BLDC motor in a correct rate. It's about 6-hour motion here. Not getting it just right. You can see the little drive circuit. It's a little controller, some MOSFETs and some drivers for them. But right here I actually got it just tuned right, and we're actually moving for 6 hours, 1/4 turn. Yeah, so that got us going to build up our first mount. Yeah. Okay, so here we have the first little version of our mount. See, I used the mounting part for the hoverboard to hold the motor, and I have a little lunchbox electronic enclosure there. Yeah, very nice. And a tripod for another mount, wood pieces to bolt things together. Yeah, that monitor stand I have as an equatorial wedge is an absolute rubbish idea. I use some dumbbell weights to act as a counterweight for the motor and the telescope or camera that I have on the motor. Yeah, and that's it. I soon started calling my little creation here the Lucid mounts. Yeah. It's basically because I have my own little company called Lucid Engineering that is absolutely not doing anything useful whatsoever, but it gave a name to it anyway, so that's what I'm going to refer to it in future videos here. Yeah. So this is my first draft, my dream mount, which is the direct drive mount, to get rid of all the mechanical issues like backlash and periodic error and all that junk. Yeah, does form its own little issues, but yeah, we'll see what we get of it. Right now it's configured as a StarTracker. Yeah, so we only have like a tripod mount here with a simple base holding up the right ascension axis. Got the control electronics there, and yeah, simple little clamp-on thing for a L mount. And well, for future things, I used to have a little polar scope right there. I need to fix the mount for it properly, but that's how it's going to be stuck in anyway. Yeah. So that's it. I'm gonna have this running, see if I can get a clock to have it sitting in view so we can see how it looks. Yeah. Okay, so here we can see that we have changed the mounting structure a little bit. It's a lot more stable. Some construction parts, yeah, that's good. Any mount should be made out of it. Anyway, a lot more stable, and we started to have this running in one sidereal rate here. I've got that little clock there standing on the base of the mount. I can see it running, and yeah, I don't know how many nights I had this running for, but it felt like it ran in one sidereal rate quite nicely. Got my hopes going, so I prepared for a night out under the sky to test it out. Yeah, here we go. So got it all set up. It's a nice summer evening, or post-summer evening, but yeah. Alright, so we are testing a very crude first version of the Lucid mount in StarTracker configuration, single RE axis. You got the motor there, you have the polar scope right there. So on a tripod, power supply and computer. Well, right now the clouds came in, so that's pretty much it for the evening. Super sensitive to winds or any movements as it is right now, but that's to be expected. Anyway, but it can track on a star. Right now it didn't have super precision. At best it was maybe with 1 arcsecond resolution, but then throwing off, so we'll have to see what we can do with this hopefully tomorrow. Yeah. Okay, after that bold statement, I think we need to look at some guide data, and we'll see that that was quite optimistic. But anyway, here is like 30-minute some guide data. So we can see, well, obviously we don't have a declination, get that out of the picture, but if we zoom in here on our right ascension, I mean, it's of course, yeah, you got spikes and it's moving everywhere, but I mean the overall, the total guide RMS is 3.4 arcseconds, which of course is due to the massive moving, but I mean the whole, what I was looking at when I gave my optimistic statement was, I mean, regions like this, I mean, where you actually have quite nice tracking for a little bit, yeah. But I mean, this is first light, yeah, first light. So I was super happy, stoked, everything. That was, I felt I was on to something here, yeah. That's it. Okay then, so final here, long episode. Sorry about that. I just felt that so much of that talk about the motor control and all that felt a bit important, because that's what the project is about. Yeah, so anyway, we built ourselves a little StarTracker out of, you know, scraps and prototype stuff and things we can find in the hardware store and all that. A little bit fun, yeah. And got it going. I was quite happy about the result. I was really keen on testing some more and all that, but we had a really bad weather curse, and it was pretty much, there was no chance to be outside. Yes. So instead of just waiting on that, well, I had another motor, I had space on the protoboard, I went on with evolution and built myself another axis for this bad boy, and yeah, so building on the Lucid mount to be a full 2-axis equatorial mount. Yeah. Well, that's the next episode. Take a look then. So, till then, may the dark side be with you.